Earth scientists study processes that occur in the intersection of the four major Earth spheres: the hydrosphere, which involves all water on Earth in solid, liquid, or vapor form; the biosphere, which involves all life on Earth; the geosphere, which involves the solid part of the Earth from its surface to its core; and the atmosphere, which involves the layer of gas that envelops the Earth. In this unit, we will focus on applications of graphs and functions. Earth scientists use these mathematical concepts to model and predict the behavior of volcanoes. Volcanoes are one of Earth's most spectacular agents of change. They create new land and provide us with geothermal energy and fertile soils. Volcanoes even influence Earth's climate. At the same time, volcanoes are also capable of profound destruction. More than 1 billion people around the world live in close proximity to an active volcano and are vulnerable to a variety of volcanic hazards. Volcanologists research when, how, and why volcanoes erupt, because understanding volcanoes is the key to keeping at-risk communities safe.
What are volcanoes? In order to answer this question, let's explore the concept of plate tectonics. The Earth is made up of layers, the core, mantle, and crust, similar to an egg. Tectonic plates consist of the crust and the uppermost mantle. Tectonic plates are cool and rigid, and they float on the warmer, softer, but still solid mantle rocks beneath. Volcanoes form as a product of transport of heat from Earth's interior. Because heat flows from hot to cold, the heat from the core and mantle rises towards the crust. Volcanoes are vents through which this heat can escape in the form of molten rock and hot gases. Volcanoes don't occur everywhere on Earth because even though Earth's mantle is hot, it takes special conditions to melt rocks.
To understand why volcanoes form where they do, we must consider the geothermal gradient compared to the melting temperature of rocks. The geothermal gradient is the increase in the temperature with increasing depth in the Earth, and can be modeled by a polynomial function. The temperature at which rocks begin to melt as a function of depth, called the solidus temperature, can be modeled by a linear function. Under normal conditions, the temperatures in Earth's mantle and crust never get hot enough to melt rocks. However, rocks can melt and volcanoes can form in three types of geologic settings: divergent boundaries, where two tectonic plates move away from each other; hot spots, which are anomalously warm zones in the mantle; and subduction zones, where one tectonic plate is pushed beneath another.
At divergent boundaries and hotspots, hot rocks rise to shallower depths rapidly enough that they do not cool down. This allows these rocks to cross the solidus and begin to melt. This type of melting is called decompression melting. At subduction zones, the downgoing plate adds water from ocean bottom sediment to the mantle, decreasing the melting temperature of rocks. This type of melting is called flux melting. The majority of subduction-related volcanism on Earth occurs in a ring around the Pacific Ocean, often referred to as the Ring of Fire.
Molten rock beneath Earth's surface is called magma. After it erupts, it is called lava. Most molten rock never makes it to the surface, and instead stalls somewhere in the crust. These subterranean magma bodies are called magma chambers and consist of a mixture of solid crystals and liquid, which we call crystal mush. When molten rock does make it to the surface, it can erupt spectacularly in a wide range of styles depending on factors such as temperature, viscosity, and gas content. Eruptions that form lava lakes and lava flows are called effusive eruptions, as lava passively rises and pours out of the volcanic vent. Effusive eruptions are common in Hawaii. Lava flows usually travel slowly, but they can flow long distances from the vent and destroy roads and houses. Therefore, volcanologists are interested in predicting how far a lava flow may travel. The maximum length a lava flow may travel can be modeled by a radical function if the volume of lava erupted per minute is known.
Eruptions can be more explosive when the lava is viscous or contains a large volume of gases. Small explosive eruptions may produce ash and throw large fragments of hot lava called bombs long distances. The trajectory of a volcanic bomb can be modeled as a parabola. Using quadratic equations, the bomb's maximum height, velocity, and distance traveled can be calculated.
The most explosive volcanic eruptions are called Plinian eruptions, after Pliny the Younger, who described the large eruption of Mount Vesuvius in 79 AD that destroyed Pompeii, Italy. Plinian eruptions produce towering columns of ash and gas, which can sometimes produce lightning. These columns can reach heights of 30 miles. The injection of gas and ash into the stratosphere can temporarily alter Earth's climate. The most dangerous products of Plinian eruptions are pyroclastic flows. Pyroclastic flows are superheated clouds of ash and gas that race down the slopes of volcanoes at speeds of 60 to 400 miles per hour, destroying everything in their path. The distance a pyroclastic flow travels as a function of time can be modeled by a linear function. This relationship is useful for assessing risks for pyroclastic flows at various distances around volcanoes. My name is Lindsay Hernandez, and I'm a petrologist and volcanologist, which means I study volcanoes and the rocks volcanoes produce to understand the plumbing systems beneath them. I'm currently a PhD student at The Ohio State University. I'm working on Fuego and Pacaya volcanoes in Guatemala, which are really active and dangerous. There are a lot of people living really close to these volcanoes, so a big part of my work in Guatemala is on improving volcanic monitoring networks so that we can warn and evacuate people before big eruptions occur. I became interested in studying volcanoes after traveling to Guatemala to visit my family. I've always been mesmerized by how mind-blowingly big and powerful volcanoes are, and they truly dominate landscapes. And it's amazing to me that volcanoes are such large parts of our societies and ecosystems because eruptions spread a lot of ash nearby, which makes soils very rich and fertile. This has driven a lot of settlement around volcanoes, which means there are a lot of people around the world who are vulnerable to volcanic eruptions. I followed a traditional path to become a volcanologist by earning a bachelor's in science and earth sciences at a four-year college and then moving on to graduate school. For my BS, I took a few courses in chemistry, calculus, and computer programming because geology is a very multidisciplinary science. The data I use comes from rocks. So I collect rock samples, I cut them into small rectangles, maybe about the size of a domino, and I glue them onto a glass slide. I then polish these little dominoes until they're thin enough for light to pass through. A microscope slide with a wafer-thin slice of rock is called a thin section. I then use an instrument called a microprobe to analyze the rock's composition. So a microprobe zaps my thin sections with a little beam of electrons. And so after this, I get a big spreadsheet of data that I then analyze to learn about volcanoes. My job is mostly office and computer work because I spend a lot of time looking at my data and trying to figure out what it's telling me about what's going on deep in the ground. I usually travel to my field sites, to my volcanoes, to collect new samples and look at new activity maybe once or twice a year. So some volcanologists do much more field work than I do, and others do less. It really depends on what you like to study. Math is definitely an important skill for my work. So for my research, I look at a lot of numbers and I build mathematical models to describe patterns that I see in my data. A lot of times I use computer programming to make calculations, sometimes using software such as Python or MATLAB. However, it's always important to understand how the functions are working to be sure that my results have meaning. I use graphs all the time for my research. Putting data on a graph is the easiest way to see if there are any patterns or relationships that can illuminate volcanic processes. Oftentimes, after I put data on a graph, I also use functions to model the patterns that are observable in the data. Functions are a really useful way to quantify patterns that we observe in natural data. Studying volcanoes is all about helping society because when we learn more about the past and current activity at a volcano, we can better predict what might happen in the future. So, for my work in Guatemala, more than 2.5 million people live within 20 miles of Fuego and Pacaya. So, learning more about these volcanoes, along with working to install new instruments to monitor their activity, will allow officials to make better decisions on when to order evacuations, which could save a lot of lives. And also, most volcanoes in the world are under researched and not very well monitored. This means that sometimes we don't have enough information to make informed decisions about where the most dangerous eruptions could happen, and that there may be little warning time before big eruptions do happen. So, the work that volcanologists and petrologists do is really important for helping society, and we can contribute to protecting some of the most vulnerable communities in the world.